A mysterious, bright flash in the cosmos puzzled scientists for over a year. But now the enigma has been unraveled. On a sunny afternoon around midday on June 13 last year, my colleagues and I were conducting routine observations of the sky when we stumbled upon what we believed to be a novel and intriguing celestial object. Utilizing a massive radio telescope, we detected a rapid and intense burst of radio waves emanating from somewhere within our galaxy. After a year of meticulous research and analysis, we finally pinpointed the source of this signal, and it turned out to be much closer to home than we ever imagined. A surprise in the outback. Our observation station is nestled in the heart of the Inyaramana Ilgaribundara, the CSIRO Murchison Radio Astronomy Observatory, located in the remote deserts of Western Australia. Here, the vast and clear night sky provides an unparalleled vantage point for exploring the universe. We were using a cutting-edge detector at the Australian Square Kilometre Array Pathfinder, ASKAP, a state-of-the-art radio telescope designed to search for rare and fleeting signals from distant galaxies, known as fast radio bursts, FRBs. The unexpected discovery. The burst we detected was peculiar because it showed no signs of dispersion, a phenomenon where different frequencies travel at slightly different speeds through space. This indicated that the burst must have originated within a few hundred light-years of Earth, placing it firmly within our Milky Way galaxy. Most FRBs, by contrast, originate from galaxies billions of light-years away. A problem arises. Fast radio bursts are among the most energetic events in the universe, releasing more energy in a millisecond than the sun does in 30 years. Despite their intensity, the mechanisms behind FRBs remain a mystery. Some theories suggest they are produced by magnetars, highly magnetized remnants of massive stars, or result from cosmic collisions between these stellar remnants. Regardless of their origin, FRBs are valuable tools for mapping the so-called missing matter in the universe. When we reviewed our data, we encountered a puzzling issue. The signal seemed to have vanished. It took 2 months of troubleshooting before we identified the problem. ASKAP, with its 36 antennas, acts like a giant zoom lens. However, just like a camera, if you try to capture something too close, the image becomes blurry. By adjusting our setup to reduce the effective size of our lens, we were able to create a clear image of the burst. A closer look. Initially, we were disappointed. The blurriness suggested that the signal was likely not an astronomical phenomenon, but rather radio frequency interference, RFI, human-made signals that can corrupt our data. RFI is a common nuisance in astronomy, often leading to false detections. However, the burst was incredibly fast, lasting only 30 nanoseconds, with a bright initial pulse followed by 2 weaker afterpulses. This was unlike any known FRB, which typically last about 10 millionths of a second. A zombie satellite? With the direction and estimated distance of the signal, we narrowed down the potential sources. The only candidate in that direction and at that distance was a 60-year-old derelict satellite called Relay 2. Launched by the United States in 1964, Relay 2 was one of the first telecommunications satellites. It ceased operations in 1965 and was declared defunct by 1967. But how could a long-dead satellite produce such a burst? Satellites, even those presumed dead, can sometimes reawaken. The most plausible explanation is an electrostatic discharge. Satellites can accumulate electrical charges in the plasma environment of space, similar to static electricity on Earth. When this charge suddenly discharges, it can produce a brief flash of radio waves. However, known electrostatic discharges last thousands of times longer than our signal and usually occur during periods of high solar activity. At the time of the burst, Earth's magnetosphere was unusually calm. Another possibility is a micrometeoroid impact, similar to the one that struck the James Webb Space Telescope in June 2022. A small piece of space debris, weighing about 22 micrograms and traveling at 20 kilometers per second, could theoretically produce such a burst. However, the probability of this happening is very low, estimated at about 1%. More sparks to come. While we can't definitively explain the source of the signal from Relay 2, we now know how to detect more such events. By searching at shorter timescales, we can identify these ultra-fast bursts more easily. This discovery highlights the importance of monitoring satellites for electrostatic discharges, especially as the number of satellites in orbit continues to grow. Finding new ways to track these satellites is crucial for maintaining the integrity of astronomical observations. But did our team uncover any new astronomical signals? Absolutely! And there are undoubtedly many more to be discovered. DM. This story originally appeared on The Conversation. Clancy William James is a senior lecturer in astronomy and astroparticle physics at Curtin University.